Welcome to my new calculus channel. My name is John Gabriel. This YouTube is the third and the last in the series called The Big Deception. So, in the previous two videos I discussed the derivative using the definition of limits. So really, what Weierstrass actually did was redefine, or try to redefine, he actually failed, but he tried to redefine the derivative in terms of a limit. And this definition that you see down here isn't really his definition, because his original definition was stated in terms of infinity, infinitesimals, and arbitrary small values. A lot of confusing terminology which really is very ill-formed. At any rate, modern academics adopted this particular definition, which is also flawed and wrong, as I shall show you in several ways it's wrong. And what you're looking at here is the demonstration of this definition. So if, for example, a certain point approaches the limit point, then this definition here is true. That is, the difference between x and c, this being x and the red point being c, x and c, is less than some delta, which is always the minimum of these two deltas as you see down here. So I've chosen the minimum in this case, and also the minimum of the epsilons. This is the epsilon value up here. Okay, so whatever epsilon value is chosen up here, I've taken the minimum. Let's just make that 999, almost 1, not a problem. So, if we move the green point in the shaded region, then we know that for all x in this interval here, in the shaded interval, we will have that this proposition here is true. In other words, delta greater than that distance implies that this distance here is less than epsilon. And so if you move out of that, even though this epsilon is still within range, it's no longer true, because this x here doesn't map into the minimum delta, which is mapped into the minimum epsilon. So anything out of this gray range here will not be true. You'll see this right arrow with across a stroke through it, meaning that this doesn't imply that the distance between f of x and L is less than epsilon, but anywhere in the gray region it does. Now, let's see what happens when we begin to do some monkey business. So, now, there's a lot of information on the screen right now, and I'll explain it all to you in a moment. So what I've done is, in this green on gray background box here, I've listed the finite difference function, which you see this straight line here is the finite difference function that is used in this calculation here. For example, if we go over here, this definition that you see here, so let's look at this for a second. This definition is how you should actually think about this particular limit here. So in other words, we replace this f of x with the finite difference, which is this, right? In other words, it's the finite difference minus L being less than epsilon, because that is how we find the derivative using this definition. Or we don't find it, we actually prove that the limit exists provided we know it. Now, Newton started with a secant line, which he would just simply approach the red point, which is a point of tangency, and at the point of tangency the finite difference is undefined. Now, what we'll do is we'll look at this red line is actually the derivative of this function here, x squared divided by 8. It's a derivative of this function. And the green line is the function of the finite difference. If we move h away, you'll see that the green line moves in that direction in a positive direction and that direction in a negative. Now, if h gets close to 0, watch what happens. Okay, the finite difference becomes undefined. Do you see that over here? It's undefined because h is 0, right? And so that's very kludgy, isn't it? Because the finite difference is what is required to show that this is the actual limit. Now, let's see where the big stupid put themselves into a lot of hot water. Using Weierstrass's definition of continuity, the big stupid would have to exclude the point at which the derivative is calculated for the purposes of not contradicting the limit definition. That is, this ubiquitous f dash of x is equal to limit as h approaches 0 of that finite difference. So, in other words, what they're saying is that over here, you have to exclude that from this definition down here, right? In other words, you're saying that x minus c distance must be greater than 0. Well, the funny thing is this, is that even though they do that initially, in order for this definition to be true, we must have that L is equal to f of c, as we see in this third definition here, in this third point. The definition is circular because it is required to know L in the definition of the derivative, and L equals to f prime of c, which is defined by this circular reasoning here, this circular definition here, and the very thing we are trying to find. Okay, so the circularity is that not only is L required to be known, but the finite difference is never defined at the point of tangency. And in normal definitions, besides this derivative definition, this particular epsilon-delta definition holds for all of them, and we don't need to have also that the function is defined at the red point. But in the case of the derivative, all of a sudden we need to have that and that the function is defined at the red point. In other words, it must be continuous at the red point, in which case we don't even need this greater than 0 sign over here, do we? We don't need this inequality to be greater than 0. It can be equal to 0 because it's got to be continuous there. Now, one of the fallacies that I showed to you in the previous videos is that the big stupid, the academics in the big stupid, try to put a hole there by multiplying it by an expression that is equal to 1. So, for example, if we wanted to put a hole in here, we'd multiply this function here by x minus 4 over x minus 4. Of course, it's not really a hole, given that that's just another form of f of x, which is not in the simplest irreducible form. But if one decides to retort that they're not the same function, that's absolute rubbish, because it's like saying 3/4 is not equal to 9/12. But we all know that that's not true. Okay, so if we have, for example, 3/4, and we multiply it by 3 over 3, we're going to get 9/12. And these are exactly the same. Okay, what they're telling you there is you have f of x and you multiply it and you get another function here, g of x. Now suddenly, when f of x was defined at x equals to k, f of g of x is not defined at x is equal to k. So that's absolute rubbish. G of x is just not in its most irreducible form. Right, so that was explained to you in the previous 2 YouTube videos. So we see here that in the first point, already they need to use brute force to have the limit L in the definition equal to f prime of c. It seems like a lot of monkey business to me, and we haven't even reached the second point yet. So what does the second point say? Well, if we look at the graph, the actual graph of what's happening here in this. Why isn't that working? Oh, I have to use this green point. If we look at what's happening here, Newton was simply just moving that point along and just finding the slope of those secants until it got very close to the red point. In which case, he said, oh, the vanishing quantities disappear, and ultimately that is the rate or the derivative at that point. So Newton was really pretty confused. So was Leibniz, and so was Cauchy, and all the other morons that came before me. None of them understood calculus. I am the first in human history to truly understand calculus at the very level that I'm explaining to you right now. And if you're smart enough, you'll actually heed my words and study what I'm telling you, because chances are you're a moron listening to this and you're thinking that I'm a crank. But I've got news for you. I am a real mathematician, and possibly one of the greatest. So I suggest you pay careful attention and stop being a moron, because what I'm telling you is true, and what you hear from your lecturers and teachers is absolute rubbish. Before my new calculus, there was no rigorous formulation of calculus. That is no longer even debatable. It is a fact. Newton's and Cauchy's calculus is a kludge. It's flawed. But I'm not just done yet. Let me not get carried away. If we move the secant line towards the red point of tangency, you'll see that it's not defined there. But that's exactly what point 2 is telling us. If h is 0, let's make h 0. Whoops. Yeah, look at that. So the green function that you see defined by this particular difference quotient disappears because it's not defined at 0, right? So this definition here never gives you the derivative. Not before, not at the point of tangency, and not after the difference quotient is simplified. In other words, it's absolute rot, it's absolute hand-waving by academic morons in the big stupid who are incompetent, ignorant, and just too dull to realize that calculus wasn't rigorous until my new calculus. And so I shall keep exposing their stupidity and treating them with the utmost contempt and loathing, because that's all they really deserve. Most of them are spineless cowards who are unable to stand up and admit that I'm correct. Of course, a few academics have admitted this, but there are the exceptions. Now, let's go back to this here and look at this point 2. The big stupid has no systematic way of finding L. Hey, you need to know L for this definition. Look, see, there's an L there. You can't not know L and use the definition. Do you understand that? Well, I hope you do. So they resort to illegal arithmetic, which you see done as Newton does in this finite difference quotient, where you're just calculating an approximation, and then they just put, after they simplify the difference quotient, they just put 0 in it, and that gives a derivative. So it's a kludge from beginning to the end. And so they're kind of happy, provided they can identify and prove it is indeed the limit. If it's not a rational number or a well-known incommensurable magnitude, such as pi or square root 2 or e, then all they have is the expression obtained from kludgy arithmetic, or a rational approximation to the same. Okay? So they never really have L, unless it is a rational a rational number or something that they recognize. Now, point 3, just to restate it again, says the definition is circular because it is required to know L, and L is equal to f prime of c. Now, things get a little more interesting when we get to point 4, because I've seen hundreds of academics wax eloquent about how rigorous the calculus is. One moron, Professor David Ulrich from Oklahoma State University, and also another moron, Anders Kaysorg from MIT, have tried to defend this, but it even fails for this implication sign here in the case of a constant function. And I'll show you that it fails. But what we really have here is that the implied connective does not work for functions such as f of x is equal to k, where k is constant. That is, the result of a true antecedent and false consequent in the proposition is false. and yet the material condition if-then requires that the proposition if-then evaluates to true always whenever the antecedent is true. So if you look at this table here, for the imply connective, the only time it is false is when the antecedent is false. And the antecedent is false in the case of a constant function, okay, as I will show you shortly. So, coming back to this here, point 5 says the finite difference function is undefined at the point of tangency, and we've seen that throughout, but it's necessary to state it because the finite difference function takes some really peculiar forms, and I'll also show that to you in a moment. First, let's look at how the imply connective doesn't work for constant functions. So we come down here to the input bar, okay, and we type in f of x is equal to 2, right? Oops, 2. And watch this. You see at the bottom here? It says this here does not imply that f of x minus L is less than epsilon. It doesn't matter where you are, okay? It doesn't matter where you are. It always doesn't imply that. So the imply connective doesn't work for constant functions, right? What I'm telling you is that the so-called morons who wax eloquent about their logical connectives and about how mathematics is really dead without their logic, or the logic that was given to us by people like Boole and Tobacco Head Bertrand Russell and all the others. That's not even required here, because ideally this should be a double implication over here, and I've always stated that this should not be a one-way implication, it should be a double implication in order to be true. But that patch, as suggested by me, still doesn't solve the problem that this is an ill-formed definition, just as ill-formed as the definition of derivative and everything else. So as you can see here, this logical connective doesn't work. It's not true. It's never true, no matter what you do for a constant function, okay? So coming back here, we've looked at the 4 points in detail. Now let's look at the 5th point here, and let's see what happens when we change the function around a little bit, so that you can get an idea of what we're talking about with respect to the finite difference. I'm going to move this along here, and also this along here, and this here, because when you're dealing with power functions, it tends to get a little hard to look at. So let's just say f of x is equal to x cubed. Let's just make that divided by 8 as well. Okay, something like that, okay? Now, a lot of information there again, but don't worry, I'll explain everything. If we look at this diagram here, let's just what's the best way to do this? Let's just get rid of, watch what happens here with the finite difference function as you get closer and closer to 0. You see that? And it's undefined again, right? So the finite difference function takes the form of the derivative, right? This green finite difference function takes the form of a derivative always, and there's no particular pattern. I mean, it just gets transformed. It's just the derivative being transformed to a different location. And so when it completely overlaps the other derivative, then supposedly you have the limit. So coming back here, we see that in this particular case you have to move this all the way along here until it's in the shaded region, and then it should be okay, right? You see that? So something else is wrong here. We'd have to readjust our epsilons so that we can do this. Yeah. So now we can move that along here in the shaded region, and it'll be okay in the shaded region, as you see here. So moving the green spot, of course we need to have the same epsilon here, and I don't have the same epsilon, so I'm going to reduce this epsilon to 2. It's harder to see though. Let's do 2.4. Let me see that properly. Okay, there, that's about right. So moving it anywhere in the green shaded, in the shaded region will be okay, as you can see by this arrow. Moving it out, it's not okay, right? And anywhere outside of those two light blue lines, it will be wrong. Yeah? But what I really wanted to show you here was not so much how this works, but this particular green function here, the finite difference function. In other words, when you get close to 0, it's not defined, right? So the same story. It doesn't matter what kind of function you have, whether it's a square or a cubic or even a quartic. Let's look at a quartic. Let's do that. Okay, so now we've got a quartic. And I'm going to have to reduce that a bit just so we can see what's going on. There we are. And now let's make epsilon more or less equal. So this is what this is. Oops, no. This is 3.39 and this is 3.52, so let's bring it down to about 3.39. Yeah. Okay, that's about close enough. That doesn't really matter. So if you move this within the green line, if it's outside here, you'll see it doesn't imply that. If you move it within the shaded region, it does imply the truth of that statement. Okay? Oops, let's move this up so we can see what's happening here. Again, see that? Alright, so, and at any rate, look at this finite difference function. It's some kind of a cubic, and it only starts resembling the other cubic as it gets close to 0, and of course naturally again when it gets to 0, it disappears, right? There's nothing there. Can you see that? It's undefined. So really what's been happening all this time is that you have a kludgy definition, and I think I want to expand that. Oh dear. Okay, how do I expand that? Let's just see. Let's magnify this. Do that and bring it down. I don't care about the rest of it because I'm gonna. Right. So if you look at that diagram there, in order to use the ill-defined limit definition, which is that, one must know the value of L. However, in order to find L, one must use the ill-defined limit definition, which is that. Okay, the common ubiquitous piece of garbage that you see appearing in thousands of textbooks worldwide, printed by thousands of morons. Now you see H, over here you see H, and now you don't. Magic, you suddenly have the derivative, okay? So the big stupid has been oblivious to these facts, has ignored them. I've been preaching this truth since 2005 to the big stupid, but a lot of them have not been able to see it, and either through sheer stupidity or arrogance, I don't know which, or maybe even both, probably both, they've not come to a knowledge of the truth, and that's pretty unfortunate. Now, this is the concluding episode of the Big Deception. My name is John Gabriel, and this is New Calculus General. I trust you have enjoyed it. Join me again next time. Goodbye.